Hello and welcome back to Hadoop Exam Learning Resources. In this session, we will be covering the Catalyst Optimizer, that is the backbone for the Spark SQL. Okay, so that is very important things. You need to understand it. This session we may have to divide in two parts. Let's see how it goes. Then based on this, we will decide it. So this PDF I'll be sharing with you. Okay, so which has handwritten notes. Okay, in it. So these are the topics which I will be covering in this. Okay, so I'll not go through in this right now. Okay, we'll cover in this detail. Okay, so what is Catalyst Optimizer? Okay, so Catalyst Optimizer, so if you know any databases or anything, so like when you run the SQL query, there is an optimizer which optimizes. You may have written query and the wrong like way, and that is not optimized, but there are some best practices which is underlying system needs to apply so that query can be executed optimally. So sometimes you write a query which can takes hours to finish, but there is a optimizer which help you to reduce the query time by the hours to the minutes or seconds level. Even Spark, in the Spark world, it is quite different actually. So like we have seen the scenario where the queries are taking like hours, and when you do this simple modification in the query or something, so based on that it will be like this hours query can be finished in the seconds. Okay, so this all can be helpful with the Catalyst Optimizer as well. So okay, so Catalyst Optimizer is written in the Scala language. Okay, so if you know the Scala language, then it would be easy to understand few of the concept which I'll be discussing. Otherwise, anyway, I'll go in detail of these concepts. Okay, so Catalyst Optimizer is based on the functional programming construct in Scala, and the main purpose of the Catalyst Optimizer is as known as optimization, so that like as soon as you add the run the query, it should be optimized internally automatically, correct? And the next is a new optimization technique if needs to be added in the Spark SQL module. That should be that should not be very complicated process. Okay, so this is a modular kind of thing, so you can add new Spark SQL optimization technique, you can add it. Or any developer, like it's more about like core developer, Spark developer team who develop the Spark framework itself, correct? One thing this, and second thing is like you as a user or consumer or using Spark framework for your own entire framework development or whatever, it's a problem solution you are running it, and you want to know like I have different data types, I have a different file formats which I need to, oh, like Spark inbuilt does not have this kind of support, correct? So if I wanted to add this kind of support, so what we can do, we can add the rules, and we can even provide the new data type support. So that is what the main intention behind the Catalyst Optimization. It support two types of optimization. We'll go in detail about this rule based optimization and cost based optimization. Where is rule based optimization applied and where is cost based optimization is applied? Okay, I'll go through this. So it is based on the Scala functional programming language. I told you it had two purposes, okay, which we have already discussed. Okay, so like adding new optimization technique which helps to adding new features to Spark SQL. Optimizer extension other than core Spark, like developer, as I discussed. So let me give you an example. Data specific rules which can push filtering or aggregation into the external storage. Suppose I am reading a data from the Oracle RDBMS and assume like Spark does not provide support for the optimization for reading the data from the Oracle database, and you are reading the entire table and you need few rows out of the table, correct? Let me draw this. Okay, so it would be easy for you. Suppose this is Oracle database, and in this there is a one table, correct, which has a millions of rows. Let's assume it from your Spark program. Okay, this is your Spark program. You connect using JDBC and you fetch the data, but you know there is some condition and you need out of this only 1000 records, but there is no technique is available to externally push the filtering on this database level or something, correct? I'm not giving the query example or something. I'm giving just an example. Like this is Oracle, obviously SQL query support and everything is there. But just to give you an example, I need 1,000 records, but there are millions of records in this table. So if this techniques are not there, if optimization technique, and if you need to develop this optimization technique, you should be able to do this. That is what the intention of the Catalyst optimizer. So that rather than sending million rows here and then filtering out getting 1,000 records, so what you can see, like huge network IO as well as disk IO is involved, correct, which is like heavily impact on your performance. So what you would do, you need to develop a technique which would push the filtering criteria to this external database or external data source, and it would help you to get 1,000 records only when and send it to the Spark framework. So what you save it here, like huge network IO and disk IO would be saved. So that is one way of the optimization you need to do this. Okay, so this kind of filtering or aggregation to the external storage can be developed, because I have to do some aggregation, some or something, correct, some if I have to do on this millions of records. So rather than bringing the data millions of records over here and then doing the sum is not a good thing, correct. What I'll do, I'll push my aggregation, uh, whatever rule is there, I would push here, do the aggregation on this data, correct, and then send the result only. So that is again save the huge network IO. So that is the basic concept behind the Hadoop framework or Spark framework. You always send a code to the data, correct. So this is pushing the aggregation, filtering or whatever is towards the data. That is what the, so this kind of techniques you should be able to adding even you for your new data source or something, correct. So Catalyst optimizer supports this too. And let's talk about the Catalyst library. Okay, Catalyst library has a main things in the Catalyst library is a tree node, very tree node. Okay, this is various kind of nodes are there, one for representing your expression, one for representing for your data or some other thing. Okay, so I'll talk to you later on, and based on that some tree would be created of your data. Okay, let's leave it little for later one. Okay, so if I have this Spark code and submit it, is what Catalyst framework does is it convert your code into the tree. Okay, so and this tree is made of a tree node objects. Okay, tree node objects would be used here to create the tree. So here you can see this is the tree would be created, and based on this various steps, phases would be applied on this tree to generate the final your final output. Will go step by step in this, but assume it you would be using tree node data structure over here from the Scala, and this would be your entire code would be converted in the Spark SQL. Whatever you have written would be converted into this tree structure, and who would convert this? This Catalyst framework would convert this, correct, and apply various rules on this. So it can helpful for relational query, which SQL you write it, it has expression rules, logical query plans. Okay, we'll talk about this little later. Okay, so whatever code you write it would be converted into the tree. Let's remember this thing. Okay, Spark code is represented as a, and that tree is known as an abstract source tree. Okay, remember this abstract source tree. Catalyst framework apply rules on those trees. On the top of Catalyst framework, another library created which is specific to relational query processing. Like SQL, we would be able to running using the Spark SQL, correct. This library is for query processing to check, create the expression, logical query plans. Rules, what are the set of rules which handle different phases of query execution. So there are different phases of our query execution, mainly four. You remember this four query, and we will do the hands-on session that time also will go through this phases. Okay, so remember this. So there are mainly four phases you need to understand while working with the Spark SQL, because it matters for you how like optimally your query can be executed. Whenever generally this kind of issue comes comes in when your query runs in the production, takes longer time, and you need to analyze it, and kind of thing, you have to do this. Okay, so analyzing the query, that is the phase one. Then logical optimization of the query, whatever you have created. Then physical planning, and from the physical planning, lot of physical plans would be created for your code, and then generate the Java bytecode out of this. So we'll go in detail for each phase. Okay, so these are the four phases you need remember. So let's first understand the basics of catalyst tree. Okay, so let's say I have an this is the Scala code written, or Python, you can assume it. Okay, so he is a one variable which hold the string Hadoop exam. Okay, now what I want, this Hadoop exam needs to be appended by the two string learning and resources, and final string should be created Hadoop exam learning resources. Correct, that is my intention. So internally Spark, when you submit this code to Spark SQL, it represent your code in this tree in this format. So what is your first attribute? It he, this would be here, and this is the operator, this is append operator in the Scala. Correct, and similarly literal learning resources, and this is another literal resources, and this is needs to be. So you can see here how your code would be converted and represented in a expression. So and this node is immutable, even in this entire tree is immutable. You cannot change this tree once it's constructed. You can create new tree out of this. Okay, so each node is immutable as well as this tree is immutable. Okay, so this is the way your tree is your code is represented here. Okay, node can be 0 or more children. Like here you can see this node has 0 children, this node has a 2 children. Correct, nodes are subclass of the Scala tree node class. Okay, so this is Scala. So what rules does here? Rules, trees are manipulated using rules. So I'll apply some rule. This is input tree, and new output tree would be generated. Because I told you it's the same tree cannot be altered. You can generate a new tree out of existing tree. So that is what we would be applying the rule and generated tree here. So tree is a Scala object here. So what are the way we can apply this? If you know the Scala programming, then you could understand this pattern matching. So like we would match the pattern, and then based on this it would iterate the tree and apply the Scala features on it, and it like it's generate the tree. Okay, so let me give you an example again. Tree for expression. Suppose this is the tree x plus 1 plus 2. This is my tree. How would you represent this? X, add this is add operation, this is add operation, 1 plus 2. Correct, this is my tree. What I finally want it, when apply the rule, this expression should become x plus 3. Correct, so these are the rule which I will be applied. So tree dot transform case, this is case is a pattern matching here. Now you can see this is the pattern matching where this two literal matches, then apply this rule. Okay, wherever you find in the tree this two literal together as a one child, one of the child, then apply this function. Okay, one of the child means the child has to be the parent has to be add. Correct, then apply this rule literal c1 plus c2 or whatever you want, give the name. So this literal should be added here. So that is the one rule. Actually you can see this is the pattern matching, because here what we matching is the two literals with having the pattern as a parent as a add. Okay, so if this case is matches, apply this rule on the entire tree. Okay, so it is possible, let's assume it, this is your tree. Okay, this is your tree. Correct, let's start this from here. This is add. Okay, this is add, this is add, this is 5. Okay, this is 6 is a child, this is 4, this is 3, this is the child. Okay, this is add function. This way your tree is represented with your initial code. Let's assume it 4, and this is 7. Now what we are saying, apply the rule wherever the pattern matches, where parent is add and child is 2 literal. So what it would generate here, this would become 4 plus 7 is 11. So convert into the 11. Correct, here this pattern matches. Correct, 5 plus 6 means make it 11. this pattern again matches it. 4 plus 3 means make it 7. Now still this pattern is matches, correct. 11 plus 7, then make it 18, correct. This make it 18. Let's assume it there is a one variable as well, x, as per our tree. Again okay, this has a two child. Okay, let's assume one is 18 and another is 11. So it would become this, using this 3 would become 29, correct. So my final x tree would be converted x plus 29, where parent would be add, and this would be x, and this would be 29. So whenever value of the x would be available, this tree would be converted into the final value, correct. So this way pattern matching happens, correct, because so my entire tree has been transformed into this format. So this applies recursively on the our tree, and finally new tree would be output is generated, correct. So that is what how it works, correct here. So attribute x and literal 3, so only part of the tree which matches are replaced. If it may be possible your tree could have something else here, correct. So let's assume it, this is our tree here, correct. This is x, this is what you are saying add, correct, a value 3, and I would say here add, instead of add there is a multiplication, correct. This is multiplication, and this is value is 3, this value is 4, and this value is 5. This pattern does not matches with my rule, correct. So this won't be converted. It is not possible to convert this tree because a pattern is not matching yet, correct. But this pattern is matching, but still this is not converted here, so we cannot apply this pattern matching on this tree, and the output of this tree would be as it is this tree, because pattern matching still is not complete. So that's the reason the same tree would be generated here, correct. So it is possible your part of the tree matches. Let's say assume it, let's create this is add, okay. Let's say this is add, and this is 4, and this is 7, correct. So 4 plus 7, so when apply the rules pattern matching, this part matches with the pattern, so make it 7, correct. This, so output would be this tree, correct, instead of this tree. Now this would be correct. So partly if you define new rule which also says multiplication of also applied, so my final tree would become like this, correct. If I say add x, correct, and this is add, we have already generated here 7, multiplication is applied, so 4 into 5 is a 20, I can say here, correct. Now this pattern still matches in my case, correct. So 7 plus 20 is 27, so new tree would be generated here, add x, and this is 27, correct, 27. So this is my final tree would be generated, because if we have right now we are assuming here only one, but if we would have another pattern matching for the multiplication as well, this expression case multiply literal c1 comma literal c2, literal c1 multiplied by literal c2, another expression in the same transform method, then my tree would have been accordingly, correct. So only part of the tree which matches is would be replaced, correct. So how this tree for things work in the catalyst operation. So these rules will be applied many times, as we have seen, until all the pattern matching are completed, correct, as we have discussed. As trees are immutable, and new tree will be created after each transformation or applying the rules which we have discussed. Now let's move to the catalyst optimizer. So this all concept run behind the scene inside the catalyst optimizer. So I'm explaining you because if you will heard lot of time this terms while we go through the Spark SQL training, okay. So catalyst optimizer is one of the tree transformation framework. So you create for your code, the tree would be created, correct, and this tree goes through various phases, and finally new tree would be generated as an output, and from that tree code would be generated, Java code would be generated, and that Java code would be executed like your for normal calculation. Okay, so let's go for the which are all four phases actually. So as we have discussed previously, there are four phases: analyzing the logical plan to resolve the references. Okay, this is rule based. Logical plan optimization, so logically optimizing the whatever the plan in the previous step created. So analyze plan we have created, so this is again rule based. Physical planning, it will generate more than one or may not, correct, and physical plan, and based on the cost, how much how expensive this plan if it executed on the Spark cluster. Based on this cost would be analyzed for each plan, and whichever the best, which take lesser time and lesser CPU or whatever. So based on that, the physical plan would be selected, and from that physical plan we will generate the code. Okay, that is bytecode, Java bytecode, and that is again rule based. So let's go through this. Each phase uses a different types of tree node. As I mentioned, everything runs in the Catalyst optimizer is a tree, and tree is made of the tree nodes. So there are various trees to represent your expression. As we have seen, expression nodes are there. Okay, to represent data types, there is a data type nodes are there. For logical operators like less than, greater than, equal to, not equal to, for that also there are operators, correct. Node for physical operations like multiplication, subtraction, etc. what you would be doing, there are nodes for this. Like we have seen, the various types of nodes are available and created in the Catalyst library. So let's move ahead with the analysis phase. In the analysis phase, so when you work with the Spark SQL, you would be either working with the data frame API or SQL query you would be writing, correct. So underlying framework would remain same, Catalyst optimizer, to execute those queries or data frame API code. So whatever way you write the code, it finally drills down to the Catalyst optimizer. So you don't have to worry about this, like if I use the API, what happen if I use the SQL query. Both that would go into the your Catalyst optimizer. So for whatever you have written the code, it would be converted into the abstract syntax tree, as we have mentioned previously. So this kind of tree would be created. Let's assume it this every child has a 2 node, okay, and a parent also has a 2 node. Here this is my tree. Converted tree is created when I run the analysis phase. This AST will have unresolved attributes. What I mean by unresolved attributes, let's assume it you have this query: select course name as name, fee plus 1000 as total fee from HE table. Okay, so this is my SQL query. Okay, this is query, and this query is converted into this tree. Okay, but now problem here is this is in the first phase now still, and Spark does not know, or Catalyst optimizer does not know the name you have given here, course name, correct, is valid or not. Is really there is a name in the file, in the course name is column is there or not there in the source data set, correct. Whatever you are saying, CSV file or your JDBC table or whatever, or Hive table or whatever, what would be the data type of this column? Correct. So during the analysis phase at the start, it does not know whether this column is valid or not, what is the data type for this table. Okay, so what it does is actually it refers to the catalog object. So if you know through Google, Hadoop Hive, there is a catalog object which represent what is the data source for this relations, what, like it's a JDBC table, or it is an external table, or it's an underlying file representing something or something. So what is the source? And it also has the schema for that, whether this call relation has this column and this data type or not. So Spark this Catalyst optimizer during the analysis phase refers to the catalog object to find it out whether this column name exists or whether this data type is valid or not. So until you find this column name is valid or not, whether this data type or not is valid or not, so this is known as an unresolved tree, correct, unresolved abstract tree. So once it is resolved by referring the catalog, correct, it would resolve all the attributes, and then this is known as catalog object. So here you can see this is my tree. I would use the catalog table and some rules, and finally convert a new tree which knows all the column types, column names are valid, and etc. If column names are not valid, then in analysis phase you will get an exception. This is does not has a valid column name. When we run the actually the SQL query, and while doing some hands-on session, you'll come across this kind of error during the analysis phase. Then you would get to know, okay, this is because there is a no data type matching or no column matching. So this is what catalyst optimizer has found it. So that's the reason. And the various kind of catalog is a extended catalog, in memory catalog. So if you even in a Spark 2.0 version onwards, you can access the Spark catalog as well. So how would you do this Spark session.catalog? When you click when you do this, you would access the catalog which holds the all the available tables, all the data source information, all the data type information. So that is currently available in the session would be available to you. So catalog is what exactly, still I'm not sure you get it or not. So let me explain you. Catalog is like, if you remember, like okay, so if I create a table, correct, one table, let's say employee table. If I created employee table, so employee table has to have underlined some resources, correct, where the data is stored in the file system. So this information should be there. So where this information is stored in catalog, that is what. So this catalog will tell you what all are the column names, what are the data types for this each column, and what is the source of this, what which file represent the source, kind of thing, correct. So this kind of information is available in the catalog for each table. Okay, for each data you do this, for each everything. So that is what this catalog is holding it. Okay, so that information will get it. So that is what in the analysis phase we will resolve all the attributes which are valid or not, and what would be their final data type, correct. So in this query here you see fee plus 1000 would be a integer data type, and this would be a course name is a valid data type, correct, a valid column name. So that is what. So check for relation in catalog table, map with the actual column name. So name as a course name is in a data file. Okay, so name so this mapping is done. Again give the unique ID to each attribute. So what we are having here, attribute course name, total fee, and this. So give them a unique ID. So rather than accessing internally, it uses the unique ID to access this, because ID would help you to uniquely identify rather than parsing and everything, correct. So it would give you more better way to optimize internally everything. Hence it can be further used for optimization. So finding the types of this expression is fee plus 1000 as a total fee is integer type. So that is what we have done is in analysis phase we have found the column name is valid, what would be its a final data type, kind of thing. So that is the analysis phase. Now let's move to the phase 2, which is logical optimization. This is a rule based optimization on logical plan. So what it does in this phase, now we have analyzed it and we have created one tree. Now we need to optimize the tree, correct. Whatever the tree from your source code is created may not be optimal, correct, and it has to go to the optimization phase. And what it does is, again, it uses various Scala features to do the optimization. This is very important for your query to be executed, and this applies the standard rules for doing the optimization. So that is, if you have coded using the RDD, you will not get all this benefit. That's the reason Spark is forcing you start using the Spark SQL rather than doing the RDD code, because you have written our code in RDD may not be optimal and may not be like perform as expected. So and you have to do various tweaking to finally. So why you want to do this? When there are standard rules and standard things are available, you would be using them. So what Scala feature it would be using? Constant folding, predicate pushdown, project pruning, and null propagation, and a boolean expression. I'll explain at the end of this session what does that mean, each thing actually. So I'll discuss it. So let's assume it, these are the Scala features which is being used by the catalyst of optimization phase. Okay, so in this it will apply all this thing, and it require new rules can be added in the phase. Okay, as I mentioned, to extend the catalyst optimizer, you can apply your own rule if you want it. So in it generate another tree. So let's assume it this is your input tree, which is analyze one. Now do the logical optimization on this tree. So these are the things which may not need to, or this is now this would be a more of an expressions, and everything would be arranged here and there, and the final optimized tree would be created here. So this is, as I mentioned previously, this is catalyst optimizer is converting tree from one format to another format. Okay, now next move to the physical planning. Okay, so this is the optimal tree we have created, and now but still this tree, but there are very, so same tree can be executed multiple ways. Okay, so now physical plan has to be created out of this, how this this my code should be executed, correct? So that is cost based optimization. Till now we have whatever previous two phases are rule based optimization. Now this is cost based optimization. What it does is it takes your logical plan, correct, optimized logical plan, you apply the physical operator, okay, which is whatever physical operation has to be done based on, and it would generate various different physical plan. Like here you can see this one with this one with this one with this, and this is many physical plans, but still based on the cost model. Now cost model will see like, okay, out of this three, which one is better? So this second one would take lesser time, lesser CPU and everything, the time space as well as the memory space, both way, it's like better to run. So it would select this plan and give you the best physical plan. Okay, so for example, let's assume it you are writing a query where you are using the joins in the query, and this there are two data set, one is a large data set and another is a small data set. If you have written RDT, you could have used your own joins, or whatever way you wanted, direct join and apply this, and you see query is running in hours and not finishing because there are millions of records. So but catalyst optimizer will help you to find it out, like why not to use the broadcast join when your one of the data set is a smaller one and another data set is a bigger one. So let's broadcast this the smaller value on the other node. If you have attended our previous course Spark training, so you would know the what is the broadcast join, correct? So broadcast join will help you to send smaller data on each node in the cluster, so that join would be efficient and each individual node would join the data and then send the final result back to the driver. Okay, so that is where this you would be using. So this is what we you can see the catalyst optimizer will say, okay, let's use the broadcast join because there is a one data set is smaller. If so that is the advantage of here using it. So this is one example here, and this catalyst optimizer for every release is being improved. Okay, that is very important thing, and this Spark is majorly used with the big data world, so it's very important, and even for machine learning and all this thing. So now this catalyst optimizer is used for this machine learning as well. Okay, underline. So remember this is very critical component to understand. Now code generation. Now finally Spark is written in Scala, and Scala is written over the Java, and so to run it has to be run on the JVM. So what we have to generate it dot class file, we have to generate it to run on the JVM, correct? But Spark is again intelligent over here. Okay, rather than using the normal Java compilation things, okay, like the way Java does it or Scala does for things, Spark has used another feature that is known as quasi codes. I'm not sure accent is correct or not for this. So we were talking about the quasi codes, correct? The Spark uses quasi codes as a Scala feature to generate the Java bytecode, and it would be simpler. If you run without the code generation, then it would be complicated. I'll tell you right now how exactly. If you run this without code generation, and if you have 100 million records, so and this expression needs to be executed, correct? So what it has does, it would do is actually it iterate over all 100 million rows and then evaluate this expression. That is not a good idea. Okay, but you whenever you write the code, you do this thing, correct? But that is what Spark developer or architect had done, is rather than iterating all this thing, do in one shot using the quasi codes features, which is like one of the compiler features kind of thing, you can say. okay, to generate the runtime code. So what it does is, rather than iterating for entire row set, it do it in one shot. Okay, so how it is done, you need to learn the quasi codes and all this thing, but that is what where the this would be very expensive. If you do row by row, using quasi codes will make code generation very simple for all the rows. It does not require copying the objects and etc. So many internal things. So I won't go in depth about this right now, because that is not important, but you understand that like code generation is very important features, and that happens at the last phase, and that the code generation you does is, that is finally your RDD, correct? RDD needs to be generated and and that RDD would be executed in finally. That is what everything drills down to the RDD, as I mentioned. Okay, so these are the four phases you have to remember, for the very important for catalyst optimization. Now let's move to the some term which we have discussed previously, like constant folding. What is this? Is a compilation technique in Scala, helps in compute the expression once for all rows. As I mentioned here, like rather than doing row by row, it does it in one shot for all the rows and not repeat this for each row. So that is what constant folding is. Obviously you need to if you go through if you know the Scala, then you would be knowing this. If you don't know, then we have a Scala training, and you can go through this. Okay, predicate pushdown. Predicate means where clause in the your SQL query, correct, or filter in the data frame API. You pass this predicates to the direct data source rather than CSV, like in CSV files, RDBMS tables, and I have explained this concept, just similar concept a few minutes back, correct? So similarly, so send the your predicates to the directly to the data source rather than bringing the data and apply the filter. I send your predicates directly to the data source, that is predicate push down. So less data should be transferred, so data will be filtered at the source only, correct, as we have discussed. Hence network IO and disk IO would be project pruning. Okay, let's assume this are 100 million rows of this structure I do have, correct? So and I wanted to know the average fee or sum of the fee. Why do you need do you think we need ID, name, and venue column, correct? We don't need it. That is project pruning. So what it does is Spark we don't need it, discard this column altogether. The way it even store the data is by default, we have discussed it, Parquet format, correct, which help you even project pruning as well. So projection pruning would help you to select only the required column. So you select this column, do the average and do the sum, and ignore that. So use data transformations and other things would be reduced, and the optimization would be very good, correct? So performance would be good. Read only required columns, correct? So that is what here mean, only required columns which needed, read it. Now physical operators. Physical operators means data frame finally converted into the RDD. That is what we would be doing. Hence all the actual operators of RDD needs to be derived. You might be writing some other API while working into the data frame, correct, doing the sum. You would be writing something else, but finally it has to be converted into the RDD API, which needs to be supported by RDD API. RDD API may not have some operator, correct? It could be similar operator with other name, okay, or add is a name. Okay, so if you say data frame API says this operator as a sum, but in your RDD world, suppose you say add, correct? So that needs to, the physical operator needs to be converted. So that is what the physical operator part, correct, converting this actual operator. So that is all about the catalyst optimizer, and you need to understand this because that is very important, and whenever you work with the Spark SQL, you will come in certainly will come across this kind of terms which we have discussed here. So and thanks for watching, and I hope you like this session. If you're watching on YouTube, don't forget to subscribe it, and even I would suggest please visit hadoopexam.com, where we have a lot of trainings material, lot of certification preparation materials. You can see we have recently launched the books as well. So these are all materials available on hadoopexam.com, and we are keep adding new materials, so it would help you to learn more, and we try to give you as concrete and as better material as possible. Okay, so thanks for watching, and please refer your friend, it would help us to grow further. Thank you.